Good morning, everyone. I want to welcome you to another multivariate statistics class. Of course, today we're going to start a new topic that we call factor analysis. We're going to use this material on Friday. So I want to welcome you to factor analysis in the outline. I'm going to walk you through our background, discussing the overview of factor analysis. And I'm also going to make a distinction between the principal component analysis that we've done before and factor analysis. So what is the difference between them? We're going to look into that. Then after that, I'm going to walk you through the specification of module, okay, in analyzing factor analysis. Factor analysis because it's a module-based analysis, so we need a module specification. I'm going to walk you through how we estimate parameters in factor analysis module, how we do factor rotation, factor scores, and I'm also going to discuss some extensions like the oblique factor module and confirmatory factor analysis. And we're going to end up, with application using the data set that we've used before, in principal component analysis. Now, I want us to listen and you ask questions where necessary. I want to provide the background now for factor analysis. Okay, so when I talk about the background, we want to talk about let's look into the definition, what it does. We also want to look into the purpose of factor analysis. Now, as you can see, the other time, in principal component analysis, we consider features, and those features are possibly correlated, and we decided to create, artificial dimensions, fewer dimensions that where each is a linear combination of the features. So principal component analysis is a dimensionality reduction technique. But let's take a look at the factor analysis. How is it different? If relationship exists among variables, our belief is that if there is no cause, there's not going to be an effect. I'm going to say that again. If there is no cause, there's not going to be an effect. So our interest here is actually to uncover, what are the driving forces, that can explain the relationship among variables. I'm going to say that again. The idea behind the factor analysis is we actually want to uncover some latent factors that are hidden. And those factors, we believe, they are the one responsible for the correlations of the variables. So correlation don't just exist, okay? If there's a correlation among returns from stocks, from different stocks in financial market, it is believed that there's a driving force, okay, that is responsible for that correlation. And that's what we mean, by what we mean here. We actually want to perform an analysis to discover the hidden factors. Okay. And that's what, if you take a look at that, I said it assumes the covariation structure among a set of variables that can be described, via a linear combination of unobservable latent variables called factors. These factors initially, they were not observed. We didn't observe them. Okay. They were actually hidden, but through factor analysis, we uncover them. So they are the underlying reason why correlation exists among variables in the first place. Okay, so when you want to talk about the purposes, we got three of them. Okay, number one is data reduction. It's sharing this same property with principal components analysis. Principal component analysis is also a data reduction technique. Factor analysis is also a dimensionality reduction technique. I'm going to say that again. Principal component analysis is a dimensionality reduction technique. And of course, factor analysis is also a dimensionality reduction technique. Let me tell you this. Why do we say it's responsible for data reduction? Because the number of hidden factors that we actually going to uncover should be less than the numbers of features. Of course, in principal component analysis, the number of artificial variables that we fabricate has to be less than the number of features. The same thing in factor analysis. In factor analysis, the numbers of hidden factors that were not observed initially, okay, that number should be less than the numbers of correlated variables. And that is what we call data reduction. Then number two is data interpretation. Let me tell you this. We actually want to identify, factors that could explain the reason why variables correlate. Okay, and that's what we mean by data interpretation. Okay, then the last purpose is theory testing. This is what make factor analysis. The third purpose is what actually make factor analysis to be different from principal component analysis. Because in factor analysis, we can actually conduct statistical inference. We can actually determine if hypothesize or factor structure fit, the observed data. And that is why it is a model base. It's a model base because we actually we can have a way to investigate how the model fits the data. Okay, so which we call so if you take a look at the two types of the factor analysis that we have, the very first one is talking about exploratory factor analysis that has to do with reduction, data reduction, where you only want to identify most important factor that we believe that explain the covariations among the variables. Then the confirmatory factor analysis is the one that involve hypothesis testing. Okay, we're trying to determine if the hypothesize, factor structure that we have actually fits the observed data. Okay, away from there. So what is the difference between factor analysis and the principal component analysis? I think it's actually going to make sense before talking about the difference. It's actually going to make sense if before of us look into the similarity, what similarity or do they actually have? Let me tell you this. The two of them, they are actually explaining the covariation. Okay. They are explaining covariations and they do this covariation or using a linear combination of variables. Okay. Now, if you remember in principal or component analysis, okay, in principal component analysis, we're actually looking for the principal component that will explain the maximum variation in the data. Also, in factor analysis, we also want to do the same. We want to identify a factor, that explain, the maximum variation, okay, in the data. Now, when you want to talk about the difference between them, okay, and I need you to pay attention, so that you can see clearly the difference between them. Okay. Now, with a factor analysis, statistical model is involved. Okay. A factor analysis, statistical model is involved. And that very statistical model will enable us to see how the observed variable is related to the underlying factor. I'm going to say that again. The model that is involved will enable us to see how each observed variable S is related to the underlying hidden factor. Okay, but uh, in principal component analysis, we do not have a statistical model. Okay, in principal component analysis, of course, we want to be able to identify, uncorrelated, or variable that I call principal component that can explain the maximum variance. So, you're actually going to see here this, the two are not the same in terms of if you take a look at what they are targeting. Okay, now uh, and that was why I make a further distinction here that the factor analysis actually make use of statistical model, but in principal component analysis we make use of linear algebra. Linear algebra of you're going to hear something like Eigen decomposition. When you hear Eigen decomposition of matrix is not statistical, it's mathematical. Just wanted to be aware of that. So the principal component analysis, focus on the composition of matrix, whether you want to talk about the Ig decomposition or you want to talk about singular value decomposition and so on like that, when you are seeking the solution of principal components. But when your purpose is actually to identify hidden factors, okay, where the hidden factors I believe, to explain, the covariation among the variables. Of course, we're actually going to be statistical in doing that because of the fact that explanation is involved. When I say model, when I say explanation, whenever a particular variable explain another variable, we need a statistical model. Okay, so that's why the factor analysis, we can actually seek the redress of factor analysis within a statistical framework. Within a statistical framework, because explanation is involved, I want to see how hidden factors explain original features that are correlated. And if the reason why I need statistical model is because I want to have allowance for the error, because it is not, I don't expect the hidden factor to explain everything. There's going to be a part that is not going to be explained that we call unexplained. So we need a statistical model to reflect that. Now, I want to go into factor analysis model because we actually focusing on relationship. Statistical model will be involved, and moving forward, we need to specify the factor analysis model, and I need you to pay attention. Now, uh, I want to believe the original variables is that x1 up to xp. The x1 up to xp, if I want to go into education, the X the X1 may be the exam score, or maybe X1 may be the performance in maths, S2 may be performance in science, S3 may be performance in physics, and X4 may be performance in maybe English, and so on like that. So X1 up to XP could be score in several subjects. Okay. And of course, you know, some subjects they're going to be correlating. I'm expecting uh, if there's a calculus among the subject, the calculus should be correlating with algebra and probably correlating. I'm expecting mathematical related subjects to be correlating with themselves, and why you know the verbal, the language, the art ones, they should be correlating with themselves. Now, because of that, we believe that we're going to have the mean for each of the variable. Of course, you're going to have an average score for each variable. And not only that, well, to explain their covariation, we're going to have a covariance matrix. We don't just do what we do. We don't just use notation for using sake. We got a reason why we use notation. You can see what we're talking about here. If you really want to understand what we're talking about, I will advise you relate to real life. I'm calling X1 up to XP. I'm referring to them as scores in subjects. Okay. And we believe that some subject correlates. And why do I want to use factor analysis? I want to use factor analysis because I believe that correlation doesn't happen by accident. I actually want to identify some hidden factors, that could explain the reason why scores of several subjects correlate. Maybe the reason why mathematics scores in maths, or maybe score in maybe algebra, calculus, anything mathematical related, they correlate is because the student have mathematical ability. Mathematical ability is actually going to be an underlying factor that we did not observe that we want to uncover. And maybe the reason why subjects like language, English, reading, writing, the reason they correlate is because what the factor that could explain all of that could be verbal ability. Okay, now how is the model going to be? This is the model, and I want to explain each of the variable in the model. Do you know what we're trying to tell the world? Okay, we're trying to relate. We're relating now. We're relating the original feature with the hidden factor. Okay, this is looking like a typical of a linear regression in statistics. Okay, the X there is the original, the observable features that may be correlating. We're actually writing that to be equal to, the average. Of course, you're going to start from somewhere. The average exists, and of course, this is the hidden factors that we actually want to uncover. And of course, we take a look at this, and that is actually loadings. The loadings is going to tell me the contribution of the factor to the variable. Okay, and of course, I'm actually going to have an error. Okay, the error here. is any type of variation that cannot be explained by the factor, by sheer factor. Okay, that very error, that's what we call specific variance. Or maybe a particular student may have more calculus ability, not just mathematical ability in general, but something specific to the subject. Okay, that is what it means. So when you take a look at what I have right now, this is looking like a deterministic part of the model, and why this is looking like a random part. Whenever we specify statistical model, it is a combination of the deterministic and the random part. The deterministic will be, it's going to handle explain variation, while the random part is going to talk about unexplained variation. Okay, you can see I'm doing justice to the variable, the time. Now, that is the definition. The head is a matrix. Okay, we have a factor or loadings, and of course F1 up to Fm, because we could have more than one factor we're going to uncover. But you know what? The number of factors should be less than the numbers of features. Okay, don't forget, factor analysis also doing the job of a dimensionality reduction. Okay, then we're going to have A1 up to EP, that we'll call the error time, which is it degenates a specific factor, not the share one. Okay, now, whenever we specify statistical model, okay, assumptions always come with the model. Okay, it's just like it is synonymous when a state establish a court. Okay, when a state establish a court, or when a jurisdiction or a district establish a court, that will be an assumption. It is not going to be all cases that happen in the country that will be trying that same court. Okay, I want to believe the court will have what they call territorial jurisdiction. Okay, now the court is only going to entertain whatever case that happen within the jurisdiction. Okay, we also have the same in statistics. When a model is specified, before I can use the model to answer a question, then we need assumptions that underline the use of the model. The moment the assumptions are violated, you cannot trust your model. Now, let's take a look at the assumptions now. Okay, we have a model. This is the model, like I said, right? Now, we actually, number one assumption, we centered on the factor. Please pay attention. Do you know this factor? Okay, the factor that we want to uncover, the hidden factor. Okay, initially we did not observe them. They are unobserved. Okay, now we actually believe, because they are unobserved, please pay attention. Because they are unobserved, then they become a random variable. Okay, now they are random variable. If they are random variable, they will follow a particular probability distribution. And we believe that the mean of the factor, because it is unobserved, the mean is 0. The variance is identity. Okay, the mean is 0. The variance is identity. Okay, an assumption is that they are uncorrelated. Okay, the factors should be uncorrelated. Okay, that is the assumption. We have a way to investigate this. Okay, now another assumptions that we want to talk about will revolve around the error in the model. The error in the model, follow a probability distribution with a mean of 0, okay, and the variance of that. This is a notation for the variance. And that's a diagonal, because you know why? We're actually gonna have so many variances. Okay, now That would denote a particular or a specific, that's a specific variance. We also have another assumptions. Okay, now let me tell you this. This guy is unobserved. Error is always unobserved. Therefore, we need an assumptions connecting the two. Assumption is that since error is unobserved and the factor is also unobserved, we expect them to be independent of each other. Independent of each other means none of that should give any statistical information about the other. So this is an assumption because they were unobserved. Okay, a model is as good as assumption putting into a model. What make model to be great is when assumption hold. So these are the assumptions. Okay, I want to do something mathematical. Do you know what I want to do here? If I have a variant, if I have a feature X, what we want to do is, because model is involved, is there a way I can actually split the covariation around the observed into, into two different components? I'm going to say that again. This is similar to what analysis of variance is talking about. The analysis of variance is the splitting of the total sources of variation around the response into several components. Components like explained variation and the unexplained variation. Now, we actually want to see that now, because in factor analysis, we want to split the total covariation around the observed into two components. We want to split that into the one that is shared and the one that is not shared, which means the one that can be explained and the one that cannot be explained. Now I need you to pay attention now. Take a look at this. You know what that guy is talking about? I want to look into the variance of all the features. If I want to look into the variance of all the features, I'm actually talking about covariance. I want to split the covariance. Now, you know that uh, for us to do that, in a univariate statistics, okay, where I only have one variable, the variance of S is equal expected value of X minus mu all squared. Do you remember this from your lower level statistics? If I have just a single variable, if I have one variable, the variance of S is expected value of X minus mu all squared. But if I have more, if I am talking about multivariate, instead of having S minus mu squared, I'm going to do this. You see that? That represent expected value of S minus mu all squared. Now, when you have that, just pay attention. From definition, we know this. We know that that guy equal to that guy. But do you remember when we stated, when we specify factor model, we actually said mu equal to mu plus L half, right? Plus the error from this equation now. What is S minus mu? S minus mu equal what? S minus mu equal LF plus the error. Does that make sense? Do you see that? So wherever I see this, I'm going to plug in this. That's what I'm doing here. That's what I'm doing here. Can you see that? I'm plugging that in. Because from the factor analysis model, if X equal to mu plus LF plus DE, then X minus mu will be equal to LF plus the E. And when that happens, now we got this guy now, right? Now, can we have a way to expand that? Okay. Now look at the way we want to distribute that. Please pay attention and see the way we're going to do it. I want to use LF here, right? To multiply the LF here, but the LF here is inside the transpose. You can see a transpose here. So it's going to be LF, LF, all transpose, right? If I want to simplify that, so this is going to be LF. If I do the transpose of a product, it's going to give me this. F transpose, L transpose. Because if I have, if from mathematical rule of algebra, the transpose of the product of A, B is B transpose A transpose. So this guy here is what you have here. You see that? Now, I'm going to use the LF to multiply E transpose here. So this one to multiply that. But don't forget that very E, there's a transpose. That's why you see this. Can you see that? Now, after you've done that, then E to multiply that. Okay. Now, if you want to use E to multiply that, you're going to have like, I'm here now. I'm here now. So that would be E, L, F, transpose. Don't forget, there's a transpose on this. Okay. Now, if I open that, it's going to be E, F transpose, L transpose, right? Which is this guy here. Can you see that? And lastly, I'm actually going to use this to multiply that. Of course, that is E transpose. And after that, please pay attention. After that, you know, uh, if you take a look at what I have here, right? Loadings, L means loadings. Loadings is not a random variable. So if you take a look at this, expectation only attracts random variable. You remember what you've done before. If I have expectation of 2x from what you've done before, what is it going to be? That will be 2 expectation of x, right? Because 2 is a constant. 2 is going to go outside the expectation. So when you take a look at here, this guy and this guy, they are not variable. They're going to come out. You see them coming out? You see this guy coming out? Then the expectation will only attract anything f, because f is a random variable, and that's why you have this guy here. Okay? The same thing here. You're going to bring L out. We're here now. We are here now, and we are here now. But you know what? Moving forward, we need to look into assumptions before we move forward. Now, I need you to pay attention. Okay? Now, when you take a look at this, what do we mean the other time? Okay, I actually have I have expected value. We have an assumption. Assumption is here. That expected value of that is our identity. Okay, and I said something the other time. Uh, expectation of factor and the error should be 0. Okay, they should be 0. And expected value of this equal to that, because this guy is the same thing as the variance. Just like in lower level statistics, the variance of the error is the same thing as expected value of the error squared. You know why? Because the variance, of the error is actually equal expected value of the error squared minus expected value of the error all squared. But you know what? Expected value of the error is 0. That's why the variance of the error is expected value of the error squared. In matrix form, it is this guy here. Okay? Now, when you apply all of that here, this guy is going to become an identity. Identity times L, and that I'm still going to have that. Okay? This guy go to 0, that guy go to 0, and this is the variance. Okay? Which is this. Now, you know what we've done now. I need you to pay attention now. What have we done? Okay, this guy, which we call the covariance, has been splitted into two components. The first component is what we call commonality. Commonality, okay? The commonality. You know what commonality mean? The commonality is a shared variance. Why this guy is a uniqueness? Because that uniqueness is the specific factor, not shared. So this is synonymous with explained and unexplained variation that we talk about. Okay, that's a mathematical way of doing that. Okay, now uh then the next thing that we want to talk about, can we investigate if there's any relationship between the feature and the factor? Of course, if I want to know whether a relationship exists between original features and the factors, the covariance should not be zero. You know what is going to happen? Can somebody tell me? Let's assume that I did the covariance here and I got zero. What is the meaning? What happened? What is the implication? What is the implication if the covariance between the original features and the factors equal to zero? You know what happened? Then you are trying to say the factor model breaks down. You're trying to say there's no relationship between the original features and the factors. Then it means there is no any factors that explain the reason why the original features correlate. That is what it means. But we are telling the world that relationship exists. We have to prove that the covariance between original feature X and the unobserved factor F, we have to prove that covariance exists. And that covariance is not zero. That covariance is the loading. Now, this is a way to prove that is a loading. Okay. Now, X and F, we can rewrite that as this guy. And the other time, based on the model, I said this guy is the same thing as this guy. Okay, now if I plug that in, okay, if I now want to multiply out, okay, if I distribute that with that, you know what it's going to have? I'm going to have expectation into LF, F transpose plus. Then I want to distribute that. This LF here, multiply that, then this E multiply that too. So I'm going to have expectation, this one and the F. Just pay attention. Now, what is the expectation, error and the factor? We expect that one to be zero. Okay. Now, when you take a look at this, F and its transpose should be equal to identity. Why? Because we expect factors as well to be orthogonal. They should be unrelated. Okay. So with that, I'm actually going to have this to be L identity, and identity multiplied by anything. I'm still going to have L, and L is a constant. It's not a variable, which is going to give me that. That's why I have this. This is to justify to the world that a covariation exists between original observable features and the factors, the unobserved features. I'm moving now. Now, I want to walk you through. I want to talk about more on the decomposition. Now, this is the variance of the old data. Okay, if you take a look at this, if you take a look at here, if you take a look at this guy here is the same thing as sum of square loadings. Sum of square loading. If I use a transpose of a matrix to multiply a matrix, I'm going to get something squared. It's going to be sum of squared. Does that make sense? So which we call commonality. So if you take a look at it here, okay, this is the commonality, this is the uniqueness, this is the total variation around, okay, and don't forget, this is that, okay, so which we call the sum of square loading, okay, and this guy is a specific variance, okay, so take a look at that. Okay, now the question now is, I've already stated factor analysis model, but you know what I want to walk you through right now. If I want to estimate, if I want to uncover factors that explain relationship among variables, there are different kind of methods that we can actually use. The first method, we can decide not to go through statistical method. We can use a principal component approach. So I'm going to walk you through three different methods that we use. Number one is principal component approach. Number two, iterated principal component approach. And the last one that is statistical that we call the method of maximum likelihood. So there are three different methods that we can use if we are seeking, if we really want to want to extract factors. But you know what I want to start with now? I want to start with the principal component approach. The principal component approach is expected to give me a approximated result because I'm actually going to be using linear algebra here. Now, the principal component, this is the way we're going to do it. Okay, the reason why principal component approach is not that great is because the principal component approach will ignore uniqueness. It will ignore the specific variance. Okay, so that's why it's not great. The principal component solution is not great for factor analysis. Now, if you want to start, okay, the question is, what are the parameters of interest that I want to figure out? I want to figure out the loadings. Don't forget factor loadings, and not only that, and the uniqueness. That's what I want. Those are the parameter in the factor analysis model. Okay, I want to figure out the factor loadings. We know the factor loadings will actually tell us the contribution of factors to the original features, and of course, the specific variance will actually tell us the variation that is not shared. And if I want to use the principal component approach, okay, what we're going to, please pay attention. To use the principal component approach, we're actually going to decompose. We're going to use eigenvalue decomposition. The whole thing, we start with the covariance. Then we decompose the covariance. When we decompose the covariance, you're going to decompose the covariance into simpler matrices where, because, it is called eigenvalue decomposition, where you're going to have eigenvector and the eigenvalues. Okay? Now, when you have eigenvectors and the eigenvalues, okay, if you now, from this, okay, you will be able to uncover what are we looking for? We're looking for this guy, eigenvector. The eigenvector, I need it because it's going to serve as my loading. Now, here I'm going to have V1, V2, and so on like that. These are my eigenvectors, eigenvectors, eigenvector. But I will need to scale my eigenvector with the standard deviation. Look at this. That guy means square root of a lambda 1. What is lambda 1? That is the variance of principal component. What is the square root? The standard deviation. So I'm scaling. So when I do the scaling, look at what I said from here, from the decomposition. I was able to get the eigenvector. Then I'm using the eigenvector here, V1, V2, up to Vn, but I have to scale that. I scale by that multiplying each eigenvector by the square root of the eigenvalue, okay? And when I do that, then I have access to my loadings. That's my loadings. That's how to get the loadings. That's what factor loadings. And after getting the factor loadings, please pay attention. After getting the factor loadings, okay, I can actually get the commonality, because to get the commonality, it is the transpose of the factor loading multiplied by that to get the commonality, sum of square, so together. And if I want to get specific variance, I will subtract, the commonality from the total variance. Okay? And that is the approach here. And if I want to know, the percentage, let's say for instance, I want to know the proportion of total sample variance explained, or what I'm going to do, because I'm using the principal component approach, I'm only going to consider the ratio of the one explained by that factor divided by the total. Now, I need you to pay attention now. This is the total variance, and this is the one. This is the one for a specific factor, the loading, the sum of square loadings for a specific factor. And don't forget, we got the sum of square loading. How do we get this? We got this from this here, this guy here. Okay? Okay? So please pay attention. Now, then we'll be able to know, which is similar to what we did in principal component analysis, where if I want to get the variance explained by a particular principal component, is going to be the ratio of the variance of that component divided by the total. Okay? So that's how to do that. Now, this approach that we just used is not the best approach. It's not optimal, because this approach ignore specific variance. Any approach that ignore specific variance is not assumed to be appropriate. Okay, now can we have a way to improve on that? The way to improve on that is to use, we are still we're still using mathematical approach. So the second approach is what we call iterated principal axis factoring method. Okay, now you know what this approach is going to do. This approach will start from correlation matrix. This approach, okay, we start from correlation matrix, because you know why? uh we have this relationship. When I subtract the specific variance from the unit from correlation matrix, I'm actually going to get commonality. Okay. Now, what this approach is going to do, this approach will start by estimating the specific variance. Don't forget the other approach, the approach of principal component that we did, that approach actually ignore the specific variance, and that is the reason why the approach is not optimal. It's not going to give us optimal solution. But the second approach is an improvement on the first approach, because this approach try to estimate specific variance. This approach does not ignore specific variance. But do you know how it's going to do that? Oh my God. The way it's going to do that is actually going to look into the inverse of the correlation. You know, if I have a correlation R, right, the inverse of the correlation, okay, is the specific variance. And it will continue to do what I call iteration, because right now this is going to be initial estimate, and after that it's now going to perform iteration. This is the iteration. Okay, it's going to start with of course, if you want to do iteration, you need a very good initial value. The initial value here is the estimate of the specific variance is actually 1 over RJJ, where RJJ is the jth, diagonal of the inverse of the correlation. Now, this is what this guy is going to do. Okay, based on this, he's actually going to compute this. This guy, he got it from here. It will now subtract this from the correlation matrix, okay? And it's going to do the updates. okay, on this, okay? And after doing the update, then it's going to continue until the specific variance doesn't change drastically, until the specific variance actually converge. Okay, this is an improvement over the first method. The first method ignore specific variance, but the second method actually did not ignore that. In fact, the second method put into consideration estimating specific variance optimally. That's a good one. But you know what? That method is not still the best method. But the best method is a statistical method. Because statistical method actually incorporate uncertainty. That is why it is the best method here. You can rule out uncertainty when you are measuring a relationship among variables. And that method in statistics that we actually want to use now is what we call the method of maximum likelihood. We are not, you are not new to the method of maximum likelihood. Okay. Now, in the method of maximum likelihood, of course, to use the method of maximum likelihood, we actually want to provide the best estimate of the parameters in the factor model. Okay. And with the belief that the model will maximally fit the data. And to be able to do that, I'm actually going to say my random variable, the original observable features, follow multivariate normal distribution. Because for me to use the method of maximum likelihood, normality is required. Normal density is required. So I want to believe if I have x1, x2 up to xp, the mean is going to have a mean, and this is going to be the variance. Please pay attention. Why is this the variance? Because this guy is that. Don't forget, the covariance, we've splitted that into this commonality plus that. Can you see that now? So that is why. So instead of me to just write xi follow normal with the mu of this and the covariance, then I'm telling the world the covariance is that. Okay, which is from factor model, which is covariance has been splitted in a factor model into commonality and the uniqueness. Now, that is what I'm going to put into my normal distribution, multivariate normal distribution. When I plug in that into, in a this is, if you take a look at this, this is the log likelihood of a multivariate normal. But wherever I see the covariance, I'm actually going to plug in this to reflect factor analysis, because the parameters in factor analysis is loading and the specific variance. Then I'm going to use my algorithm, iterative algorithm, to maximize that. Okay. Since we're going to make use of this material on Friday, I think I'm going to stop here. Then I'm going to continue, uh, you know, from that on Friday. That's all what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.